Hi, this is the final presentation for Purdue ME Summer Research Project Group R03 for our project Data-Driven Modeling of Additively Manufactured Metal Parts. Our faculty advisor was Dr. Shin, and our graduate PhD student assistant was Zhang. So to begin with our problem definition, additive manufacturing has introduced many new technologies to the manufacturing industry. Recently, AM metal parts have shown promise in the fields of rapid prototyping and small volume production runs. Each technique produces parts of differing qualities and with different properties, and tensile testing for all of these combinations is expensive and time-consuming. Companies cannot afford to collect expansive amounts of data for every combination available. In order to sustain progress in the field of additive manufacturing, better modeling technology is required to reduce costs related to process and material testing. Our team's goal was to collect and use available scans of AM metal parts to generate a data-driven model capable of determining the relationships between microstructural and mechanical properties and using these relationships to accurately and consistently predict physical properties from given microstructural data. In order to provide a simple and cost-effective method of predicting AM metal part performance, the team set out to collect data on 4 metals and 4 AM processes. Below you can see who worked on each process and material combination. After collecting data on these material and process combinations, focus was set to shift towards developing a data-driven model for property prediction using neural networks in MATLAB.
So in order to bypass the need for the expensive in-lab equipment for mechanical testing, our group pursued the use of a shallow neural network to relate the component microstructures to the corresponding mechanical properties of those components. And so the neural network, they're designed to recognize patterns, often nonlinear, within input data sets, which is perfect for us. And so we wanted to train a feed-forward neural network to recognize patterns within the component microstructures to predict the mechanical properties. And without access to in-lab equipment working this summer and working virtually, a vast amount of research was completed within the first 5 to 6 weeks of the project to collect enough data in the published additive manufacturing research studies to effectively train a neural network. And in the last weeks of the project, it involved processing all the collected data and microstructure images for input into the neural network and finding the optimal structure for the network. So the first 6 weeks of research provided the additive manufacturing studies along with the microstructure images and corresponding mechanical properties. And we needed to process those microstructure images using the ImageJ software suite to isolate the grain boundary maps. And this was done through various image processing techniques, and using the analyze function in the ImageJ software, we're able to find grain size distributions for all the microstructure images. In order to generate more data points for the neural network training, we used the GIMP software to split the microstructures into smaller sample sizes, and each sample was matched with the set of mechanical properties of the parent image to create new data points. The samples were either divided into 9 new images or 16 new images, just depending on the number of grains included in each section. However, on average, around 50 to 70 grains were included in each subimage. And the same steps were used in order to analyze and then generate grain distributions for the smaller subimages, which were later input into the neural network for training.
To train an effective neural network, we normalized all microstructure grain distributions according to percentage of grains falling into respective grain size bins. These 11 grain size bins per sample became the inputs for our neural network with corresponding mechanical properties as the targeted outputs. We experimented with various hidden layers, training algorithms, and data partitions for validation and testing sets to find optimal network structure. Example neural network training results can be seen for the stainless steel 316 material and laser powder bed fusion process, using the Levenberg Marquardt algorithm, which used 10 hidden nodes and 285 UTS data points, with 80% training and 15% validation. This network was attempting to predict ultimate tensile strength values for a stainless steel 316 component based upon its microstructure. Minimal amount of overtraining near the end of the MSE plot can be seen by the slight rise in testing and training MSE values. As such, this network provided an adequate model for predicting mechanical properties.
So from this project, we had a couple outcomes, including that we were able to amass a good amount of data from the research articles which we pulled from, including EBSD and SEM images, as well as the microstructure mechanical property data which is associated with these images. And we were also able to summarize these research papers and conduct extensive research as well as documentation on our process for future work. And so this project provides a great basis for future work, wherein that we can collect more images and more microstructure and mechanical property data and actually improve the predictive model of the neural network and produce higher levels of accuracy in the neural network. And what this will allow is for the industry to be able to use this neural network and rather than spending a lot of money on doing tensile testing and just mechanical property testing on their parts, what they can do is use this neural network to be able to predict the mechanical property data which is associated with the microstructure data which they will already have.